Our work is entitled Weekly Supervised Semantic Segmentation Learning on UAV Video Sequences. The domain of scene understanding from unmanned aerial vehicles is of high interest for researchers in the computer vision domain, since it can be used for object detection and tracking in scenarios like deforestation monitoring, traffic surveillance, or for civil engineering tasks. However, the topic of dense video segmentation from drones has been insufficiently explored due to the lack of annotated ground truth data. Previous methodologies range from straightforward 10-layer networks for scene classification from videos to more complex frameworks like spatiotemporal fully convolutional network, which uses LSTM to define temporal features, while spatial maps are used to infer future information. To deal with the redundancy encountered in videos, light-efficient and real-time network was introduced, which is based on feature propagation and holistic attention. Lately, self-attention and bidirectional GRU modules are combined to improve the results of semantic segmentation in dynamic scenes. Expanding on previous work related to gated recurrent flow propagation, we propose a solution based on semantic segmentation and optical flow neural networks, linked together by an improved spatiotemporal GRU component, to efficiently solve the problem of weakly supervised semantic segmentation of video sequences recorded from drones in an end-to-end fashion. We use the gated recurrent flow propagation framework, which takes the semantic segmentation from the previous frame, uses the optical flow to warp it to the current timestamp, and feeds it together with the previous and current color images to a spatiotemporal GRU component that corrects and refines the semantic segmentation prediction. The novelty of our work comes from the employment of depth-wise separable convolutions for the GRU component, which decreases the computation time with 25% and increases the segmentation accuracy by 0.5%. We approach this from a weakly supervised learning perspective and perform several experiments that allow us to obtain the optimal quantity of necessary ground truth data for training. We present an overview in terms of network performance for all components, results which were obtained with an NVIDIA 1080 GPU on square images with size of 512 pixels. For the static segmentation component, we took into consideration ERFnet and HRNet. Even though the mean intersection over union is better for the second network, its runtime is higher since the model also has more parameters. Looking at the runtime for various RNN components, we notice that our implementation of GRU with depth-wise separable convolutions performs better than the original implementation of LSTM and GRU, both in terms of runtime speed and segmentation accuracy. We also observed that for the optical flow generation, VCN performs better than PWCnet, both in terms of runtime and accuracy. The advantages VCN brings over other similar networks are faster convergence and improved generalization capabilities. Therefore, it is more suited for an end-to-end training scenario. To further train and test the network, we use MIDAIR, which is a large synthetic dataset of realistic images recorded from a drone perspective. We trained both the original and the proposed frameworks using every Kate label. The performance of the network decreases with the sampling rate as expected. However, we noticed that using the STGRU component improves the segmentation prediction, no matter which percentage of the dataset we employ. For example, comparable mean IOU results can be noticed between GRU8 and ERFnet 4. To further test the end-to-end framework, we compared the results obtained when using the two optical flow networks. We noticed an improvement in the segmentation prediction for classes like ground vegetation, rocky ground, boulders, and road sign. Overall, the end-to-end network performs better compared to the static segmentation at the cost of an increased computational time. In conclusion, we presented a weakly supervised semantic segmentation network for video sequences recorded from UAVs, which is more accurate compared to static networks when using lower percentages of training data. Our proposed framework improves the accuracy with 3.3% on average for the video semantic segmentation task and with 3.7% on an end-to-end training scenario.